can start?
Yeah, I think we can make a start now.
Okay. So welcome everyone. It's a while since we've had a Research Software Network meeting. Life's been put on hold a bit, but we're giving an online meeting a go, and we've got 36 people in the room, so looks like it's hopefully going to be reasonably successful. And so I'm going to hand over to Bob, who's fairly recently joined the university in the computer science department, and is going to do his talk on data visualization. So I think everybody's got their video and microphones turned off and muted, so that's great. But Bob is happy to take questions as he goes along if anyone wants to just turn their microphone on and ask a question. And I will also keep an eye on the chat if anyone wants to type a question in as we go along. And we'll see how we go. So I'll hand over to Bob. And I just remembered we are recording, so hopefully that's okay with everyone.
So thank you, Luis, for inviting me to give this virtual talk. This is the first time that I've given a talk under these circumstances, let's say. So thank you again, I really appreciate it. Also, this talk is not going to follow the traditional format of a talk. So it's in a non-traditional setting, and it's going to be a non-traditional format. So the traditional format of a talk is just slide after slide from start to finish, like the perfect recipe for sleeping, essentially. This talk is not going to follow that format. We are going to use a combination of slides, but I'm also going to include demo videos. And basically what I'm going to do is I'm going to use slides to introduce the topic of data visualization. And then at some point, I'm going to have a slide that presents 9 different options. And those are 9 different directions that the talk can go into. And I will actually be asking the audience to pick the direction that we go in. So you'll actually have to vote. So this is going to be a very interesting experiment. And I'm trying also to pay attention to the comments in the chat. Can everybody hear me? So somebody said they can hear me, but somebody said they're having trouble. Luis, you can hear me, right?
Yeah, I can hear you.
Okay, great. I just got a new microphone 10 minutes before this talk. Also, I encourage anybody to interrupt me at any time. So you can ask a question at any time. You can turn on your microphone. You can start screaming. Like, do whatever you want. I would prefer that there is some audience participation. And that's the way I am in the physical, real world too. I encourage people to interrupt me, to throw rotten vegetables at me, whatever they feel like doing, just go ahead and do it. Okay, so the title of this talk is called Data Visualization Development in the COVID Economy. My name is Bob Laramie. And since I'm new to this community, I thought I would just give some background about myself. So I was born in Boston, Massachusetts. I don't know if anybody here knows what people from Massachusetts are called. I got a degree in physics from the University of Massachusetts Amherst. Has anybody ever heard of UMass Amherst? Oh, that will be my first test of the audience. Okay, so far nobody's ever heard of it. Okay, at least one person has. Good, good. And after that, I studied computer science at the University of New Hampshire in Durham, New Hampshire. This is back in the US. And you'll see that there is a dashed line there and then an arrow that represents the Atlantic Ocean. So from going to the University of New Hampshire in Durham, New Hampshire, I jumped across to Austria and wrote a PhD at the Vienna University of Technology. And that was in computer science with a specialization in data visualization. And from there, I jumped again across the English Channel to Swansea University. And then I joined University of Nottingham just in January, February of this year. So very, very recently. And then a few weeks later, this whole lockdown happened. Oh, somebody did their postdoc in Boston. That's very impressive. Very, where in Boston? Which institute? This is Christopher Madam. Boston College. Okay, yep. Last I checked, Boston College is pretty expensive. I think my dad has a degree from Boston College. Okay, so let's talk about data visualization and why it's an interesting subject. It's really evident now. I don't think it requires too much explanation as to why it's important now, but I will give some explanation anyways. So this diagram that we see now is basically an evolution of thought, or a thought pattern. And it's a thought pattern that is more and more ubiquitous as time goes on. I would say it's quite ubiquitous by now. So it starts with a real world challenge. We all have real world challenges that we're facing. We have problems we're trying to solve. We have goals we're trying to reach. We have experiments we're trying to conduct. And for all those real world challenges, there's usually a physical or analog approach. So for example, if I want to build a car, I could theoretically get out a set of tools in a factory and literally put together a car. However, generally speaking, especially in the car example, what prevents me from putting together a car is that it's not feasible. For a lot of our real-world challenges, the physical approaches or the physical solutions are not feasible. I cannot afford, for example, to put together a car. If I was a marine biologist, for example, I cannot literally follow around wild sea life and observe them. That's physically not possible, especially if they're deep sea wildlife. Right? If they dive too deep, I can't follow them. I can't hire a submarine if I want to observe them. Even if I was able to hire a submarine and follow a whale around, for example, or some other deep sea wildlife, the mere fact that I'm observing the undersea wildlife would change the behavior of that which I'm trying to observe. So it starts with a real-world challenge. There are physical solutions and approaches to real-world challenges. A lot of them are not feasible. So what do? We jump across this dashed line. That dashed line represents the transition from the physical world into the digital world. So we're constantly looking for software solutions or digital solutions to our problems. For example, we want to develop a mobile phone app to help solve our problems. Right? If we need a taxi, we can develop an app like Uber, and that gives us a digital solution to a physical problem, which is finding a taxi, for example, and finding a taxi driver. But the digital solutions to these problems lead to a new set of challenges and a new set of problems that I call data chaos. Right? For every digital solution that exists, there's usually a set of associated data that accumulates and accumulates, And at some point it becomes so large and so complicated and such high dimensional data that it creates chaos, right? We suddenly see that there's a gap between our ability to collect data and our ability to extract meaningful information and utility from the data. And that's what visualization is here to help with, to solve. It takes the data chaos and turns it into something that we can understand, we can see, right? Data is not very useful if you can't see it. And funny enough, most data is unobserved. Nobody ever sees it. That's the majority of data out there. And I call this the visualization cosmos. Right? We go from chaos, the data chaos, to the visualization cosmos. Right? Sounds a little bit philosophical. It is a little bit philosophical. And this is happening, it doesn't really matter where you look, this is happening everywhere. Right? Here are just some examples of where this is happening, right? If you're an engineer, you collect CFD simulation data, and if you do collect CFD simulation data, you realize that this is a massive problem. Right? Simulation data is huge, and it's very difficult to analyze, and extract useful knowledge and information from. If you're a physicist or an astronomer, you're collecting lots and lots of data through experiments and maybe images, like satellite images, for example. Marine biologists collect a lot of data through accelerometers or other tracking devices, sensor devices that they attach to wildlife, or biochemists running simulations like computational biology, for example. Physiologists, sociologists, and so on. These are just one of hundreds of examples, a few of hundreds of examples. Sports scientists, right? Their data is video. They record sporting events, and afterwards they watch the videos to try to extract information from them. That's a form of data. We can also look at text, like the journalists and the humanities. Everything that's written down can be considered a data set. So you walk into a library. I look at a library as just a humongous data set. We also have, right now, this is particularly relevant, we have governments and councils collecting public sector data, right? So these are, on the left side of this slide, these are all kind of professional, these are professions that collect the data for a living. That is part of their job. And on the right, this is more individualized. This is data that's being collected about you on a kind of individual level. This is your day-to-day experience, like banks, right? You go to the bank and all of your bank transactions are archived. If you pick up the phone and you call somebody, that information is stored in a database. If you go shopping, all of that information is stored, right? Because to try to figure out when the best time to open your store is. Every time you visit a web page, that data is recorded somewhere, at least two or three places. Every time you take public transport, that data is recorded somewhere. Particularly relevant right now is healthcare data, right? The NHS is collecting lots and lots of healthcare data right now. Public Health England is collecting lots and lots of healthcare data. And these are all stored in electronic health records. And then you have individual data, right? You also collect data. You collect photos. I collect selfies, right? I have a collection of 20 million selfies on my phone. People collect videos. They collect files. And of course, now we're kind of absorbing, a lot of us are in this state where we're absorbing the data from the media, right? We're absorbing the media, and that's another form of data. So really, no matter where you look, everybody's collecting and collecting data, both in their personal lives and in their professional lives. And this is all part of the data chaos that I mentioned in the previous slide. And I think this is also, I have a theory that people just like to collect. This is part of human nature, just to collect things. I think that maybe this is a leftover kind of consequence. It used to be at some point it was a survival mechanism, and now we just collect for fun. Sometimes people are collecting things and they have no specific purpose for collecting those things. Everybody with me so far? This is sort of a tribute to the current situation that we're in. I'm going to mention numbers and semantic dimensions. This is a topic that people very, very rarely talk about, even though it's really, really important. So one of the types of data that people like to collect is just numbers and counting things. And one of the things that basically the let's say the untrained eye, or the layman, if you will, or the average person, I don't know how you want to call that, but when an average, let's say an average person looks at a number, they immediately assume high certainty and high accuracy. So that's represented on this graph. This is a graph of numbers in semantic dimensions. So along the x-axis is this dimension called certainty, right? As I go towards the right, certainty increases. You can also think of this as confidence. So this is one of the semantic dimensions of numbers and numerical data, is certainty. Every number has a certainty or a confidence level associated with it, right? So as I go further to the right in this space, the certainty increases. And as I go to the left, the certainty decreases, or it's called uncertain, right? In this, the way I've represented it here. There's another semantic dimension called accuracy, and that's represented on the y-axis here. So as the y value or the y-coordinate increases in this graph, accuracy also increases. This is another semantic dimension to numerical data or any data, it doesn't really matter. There are more semantic dimensions. These are only two of them, but that could be a special lecture in itself, just semantic dimensions of numbers and data. But I chose these two because they're particularly relevant today. And when we see a number, what we usually do is we assume in the top right-hand corner of this space, numeric data is usually interpreted with high certainty and high accuracy, or it's very certain and very inaccurate. Numbers, when you see a number, that's the implied message. Numbers imply certainty and numbers imply accuracy. There's an implicit message in there. And that's probably, essentially, that's leaving out some important information. If you see a number and that number has no confidence associated with it and no accuracy associated with it, then some information is missing there. When I studied physics at the University of Massachusetts, this information and this practice was drilled into our heads ad infinitum. So if we submitted homework, or if we wrote a test, or if we conducted an experiment and we wrote down any numbers and the numbers were not reported with certainty and accuracy information alongside them, points were taken away from us. We were penalized. So after that degree of training, it was automatic that all of our numbers, and you can see them in many circumstances with this plus and minus symbols, right? A range of values where the lower bounds represents the minimum possible value and the upper bound represents the maximum possible value, and then there's a range in between that implies the accuracy and the certainty. And then when I left physics and went to computer science, all the uncertainty and accuracy information disappeared again. And I thought, wow, this is amazing. There's a whole area of science where the uncertainty is now left out again. So that kind of experience, changed the way that I look at numbers, right? And anybody that's in the sciences that deals with measuring equipment will be very, very familiar with this principle. I'll go over just some examples. One example. So imagine this is a data set where we're counting, and it's the census. So imagine we're trying to figure out how many people live in the UK, right? This is an exercise that happens, I think, every 10 years. I think the last census might have been 2011. So you might think that this is not a difficult exercise. What we're trying to do is we're trying to count the number of people living in each house, right? So imagine we see the number 2, right? We think, okay, 2 people live in a house. And if we just look at that number 2, there's no certainty associated with that, or the certainty looks very high because it's implied there, and the accuracy looks very high because we just see that number. But if we look a little bit more carefully, there is certainty associated with this number, and there's uncertainty associated with the number, and there's accuracy associated with the number, and there's inaccuracy also associated with the number. So along the certainty dimension, what increases the uncertainty is when we start to define the terminology like, what does it mean to live in a house? Right, we have to somehow define that. How often do we have to be there in order for it to fit the definition of living in a house? Do we need to be there a certain number of hours per day? Do we need to be there a certain number of days per week? Do we need to be there a certain number of months per year? Yes, it's not difficult to see how relevant this is in today's economy, so to speak. Also, how long do we have to live somewhere in order to be counted in a house for a census? How long? Do we have to live there for a day? Do we have to live there for a week? Do we have to live there for a month? I think the legal definition might be 6 months, but I've forgotten. Also, what if somebody has just moved in or just moved out? What is the cutoff threshold? If they moved in yesterday, do they count? If they move in that day, do they count? Or if somebody moves out on the day that the census is occurring, do they count? Which household do they fit in, right? Can one person occupy more than one residency, right? So I'm asking all these questions because they all pertain to certainty. When we see a census and we see, okay, 2 people live in this house, there's no information about the certainty and uncertainty there. All of these questions and all of these definitions are going to affect the certainty axis or the uncertainty axis along X there. In other words, there's an uncertainty there that's generally ignored. That's generally what I'm saying here. The uncertainty in this number is generally ignored. Some questions that might affect the accuracy of a census. For example, are there any household members not reported? Right? Some people might want to have some residents in their house that are not reported for who knows what reasons. Also, the census is often done using reports. So a person will fill out a report, right? They may leave somebody out, right? Or maybe they even add a fictitious person. I don't know why you'd want to add a fictitious person. Maybe there's a tax benefit or something. But I can imagine it's possible, and there might exist some reasons to do that. What if somebody is 9 months pregnant? How do they count? Do they count as one person? Do they count as two people? What if they're pregnant with twins? Does that count as 3 people? And you might think, oh, well, that's an unusual situation. No, actually, that's a very, very common situation because the birth rate is above 1%. Right? If the UK has 60 million people, I don't know exactly how many people it has, 60, 70 million people, that means 60,000 to 70,000 births. That means there are going to be way larger than that number of pregnant people, right? At 9 months pregnant, there might be more than 60,000 people that are more than 9 months pregnant. That's going to affect the accuracy axis, the y-axis of the census. And there's also human error, right? The census information is collected by people. People have accidents. They write down the wrong numbers sometimes. Even I do it sometimes. And I often get complaints that somebody can't read my writing. That's very, very common. So these are just 2 semantic dimensions of data that are good to keep in mind, that are very important and are usually ignored, I would say. Okay, so let's move on. And if anybody has questions or comments, interrupt anytime. I see a comment from Simon here as well. Yeah. That's right. So you can see it's not very difficult to imagine the consequences of the uncertainty and the accuracy. For example, the number of predicted COVID deaths, there were predictions made, right, by various universities and various academic institutions, and they all had different predictions, right? None of the predictions were exactly the same. Some of the predictions included uncertainty information in them, which is very good. It's good if you see predictions of values and they include uncertainty information with them. So I have seen some of those during this time. But if you look at, say, the mass media, that information is usually left out. So what is data visualization good for? These are 5 interesting aspects of data visualization, 5 advantages, let's say. Data visualization is good for exploration. This is the case when you are looking at a data set maybe for the first time. You're not an expert in that area. You didn't actually collect the data yourself. You just want to find out what's in the data set. If there are any patterns, any trends, you might just be trying to figure out what the data set is. And you want a tool that lets you explore it, basically, and see it from several different angles. Analysis is the case when you are conducting some sort of an experiment, usually. And this is when you are the person who's collecting some data, and you're collecting that data because you're trying to answer specific questions, or you're trying to test or refute a very specific hypothesis. Like, I believe that there are more than 60 million people in the UK, right? That's a hypothesis. So you might take a census to try to confirm that hypothesis or refute that hypothesis. I think presentation is what most people associate with data visualization. So that is when you've got your exploration is kind of finished, let's say, or your analysis is finished, and then you want to communicate those results to a wider audience, right? Like a set of managers, your boss. Today I'm going to try to do some of that, and so on, a wider audience that of non-experts. Some more subtle advantages that DataViz offers is, one is acceleration. This is not as obvious. Now, what does that mean? There is essentially one process that we all do with data. Everybody in the world. Anybody? It's a difficult question. Anybody want to guess what we usually do, what everybody in the world does with data? It's more difficult to ask questions and get answers over the virtual format. There is one action that everybody takes with all data. Exactly. Well done, Joseph. Are you cheating? Did I tell you that already? Search. Searching is, throw it away is a good one. Delete it. I got delete as an answer once to that question. But searching, yes, everybody searches the data. So data visualization can accelerate the search process dramatically, right? So data visualization can make some searches possible that were previously impossible. Or some searches that used to take months can be reduced to just a few seconds. And I'm not exaggerating, that's really true. And the other subtle aspect is increasing confidence. So when you can see your data that you're collecting, your confidence level increases. It increases for at least two reasons. One is data visualization often highlights systematic error. So if you're making some sort of error during your data collection process, those errors pop out very quickly as soon as you start to generate pictures of it. But on the same side, on the other side of that same coin is, as soon as you start to see pictures of your data, you are also more confident that what you're doing is correct, right? You see the behavior that you're expecting, and that increases your confidence. You could say it increases your certainty, right? So those are 5 great advantages that DataViz offers. Okay, so this is the non-traditional part of the talk. This is the part where we have to, as an audience, as a collection, make a decision about which direction the talk is going to go into. What I'm going to do is I'm going to give, say, a 60-second, 1 to 2 minute description of each direction. And then we're going to try to take a virtual vote on which direction to go in. So get ready to vote on which topic you would like me to talk about. So there are 9 different topics here. And each one of these topics is something we're working on or have worked on. And they all have video demonstrations associated with them. But we can't talk about all 9 of them because it would take way too long. Maybe we can talk about 1, or maybe we can talk about 2, possibly, we'll see. But we will probably only talk about 1 to 2, and therefore I'm going to let the audience vote. Yes, I could try that. We could do, yeah, maybe I should add each topic to the chat. That might be a good thing to do. Actually, I should get a notepad here. And I haven't even said what the topics are yet. And people are, I have to, I'm going to take a notepad here to start recording votes. So we have, hold on, I am going to describe them.
I'll just put the subjects in the thing, and then people can just do a thumbs up, and it'll count them for us.
Oh, really?
That'll work.
Okay.
Yeah, so you'll be able to see how many thumbs up there are when I manage to type them all in.
Okay. HD engine and then literacy. So I'm just trying to, so we already got one for HDV, high dimensional viz. We got 2 votes for high dimensional viz already. Smart City Viz has one. Digital Humanities has one. Bioscience has one. You can vote more than once, by the way. So Smart City Visualization is, maybe there are people that are already familiar with this topic, but there's more and more pressure on governments and city councils to make the most effective use of council and governmental resources. Right, the population of cities is increasing, but it's increasing twofold. It's increasing threefold actually. So one is that the population is increasing generally. The second is more and more people are moving into cities, out of urban rural areas into the cities. And there's the aging population. So all 3 of these factors combined puts more and more pressure on cities to make the most effective use of their resources. And how you do that, you can use digital strategies to make your cities more resource efficient. And so smart city visualization is that topic. Marine biology, I kind of already mentioned that already. That is about using sensors and attaching them to wild marine life and then letting the marine wildlife loose into the wild and then recapturing the animal either a few hours or a few days later and trying to figure out what that animal did. Very non-trivial project. The third one is call centers. So understanding the behavior of the agents. The agents are the people that work in the call centers. Trying to understand their behavior. And that's a business setting. So there's a business-related project that we're working on. Then the visual digital humanities is about, essentially that is text visualization. How do you visualize texts? In this case, we're looking at translations of Shakespeare's Othello and trying to figure out how the translations relate to each other. Where do they change? Where are they stable and where are they unstable? Sometimes when you translate Shakespeare into German, the variance in the translation is very much open to interpretation. And we looked into ways to visualize that. Visualization of population healthcare data, that is, so everybody here knows that the Public Health England is collecting data about the health of the UK, which happens to be particularly relevant at this time. It's a high-dimensional data set, right? People suffer from many different illnesses. And how do you visualize that in an effective way and in a way that also combines geospatial information? That's what that one is about. Computational biology. This is the study of life at the molecular level and at the individual molecules and individual atom level. So this is a simulation. This is a set of simulations, and we did some visualization of computational biology data with Oxford University. They have a massive group there, all generating lots and lots of simulations of proteins and lipids, protein-lipid interaction. Then the next one is high-dimensional visualization. This is a more generic, this is what you might call basic research. So how do you visualize data that has 10 dimensions or 20 dimensions? And what happens when the size of that data set is millions of records, for example? That's a generic basic research technique. And then the next one is virtual engineering, the study of the combustion engine. So lots of people dedicate their lives to optimizing the combustion process inside of the combustion engine. And how can we use visualization to help with that optimization? That's that one. And then the final one is data visualization literacy. So we're working on we're working on experiments that investigate barriers to data visualization literacy. What is it? What aspects are there about data visualization that prevent people from interpreting the images that they see correctly? This is another one of our ongoing projects. Okay, so now I guess let me just count here. I can see I've already lost some of the counts. Okay, I see. So for high dimensional, oh, I see. You can click the thumbs up for each topic. I didn't know that. So we have 17 that have voted for high dimensional visualization apparently. And we have 4 for smart city. There's one here, count the thumbs up. Okay, yep, I'm trying to count the thumbs up. Visual digital humanities is 5. Good that there are people watching. I wasn't sure if anybody was actually going to watch today. The bioscience 1. Population health.
46 people watching at the moment.
Okay, way more than I expected.
It's good.
Motor simulation is 6 so far. Computational biology is also 6 so far. Data viz literacy is 11. Okay, anybody else want to vote? That looks like somewhere around 40 votes right there. So that's pretty good. Looks like everybody voted, or nearly everybody. I must say I'm a little bit surprised that it seems that the high dimensional viz got the most votes. I don't mind, it's absolutely fine. I think this might, I'm trying to remember, this might be the first time that high dimensional viz got the most votes in the first round of voting. Okay, so I guess we're going to talk, surprisingly that experiment seems to have worked. So I guess we're going to talk about high dimensional visualization. This is always a relevant topic, always. And I think for some people this might be very educational. But before I forget, some of you might be interested in these topics or other topics. You can find out about all of these topics on we have set up a data visualization YouTube channel. I'll just show that very quickly. We do have a data visualization YouTube channel, right? If you search for my name or DataViz Bob, you will find the YouTube channel. And you can find videos about all of these topics on the DataViz YouTube channel. So if there's some topic that you really wanted to see that we don't talk about today, it's absolutely no problem, right? You can see there's a visualization literacy category. There's geospatial visualization. The smart city viz will fit in there. There's visualization of call center data. So all of these topics are covered already on the DataViz YouTube channel. So don't feel like you missed out, let's say. If you want, you can take take a whole class on data visualization. You can watch all the lectures from 2019. I've been recording my lectures for a few years now. You can watch all the ones from 2018 as well. So there's a lot of stuff there to see, and all of these topics are represented on the DataViz YouTube channel. Look, there's molecular dynamics visualization. There's the visualization of Shakespeare's Othello and so on. So even if we don't cover a topic, you can find all those topics on the DataViz YouTube channel. Okay, so a little introduction to high-dimensional visualization. We do have some slides for this topic. So we're gonna briefly talk about, give a short introduction to parallel coordinates. So parallel coordinates are a high-dimensional visualization technique. And the basic idea is we start out with a data set with n dimensions or attributes. That n can be whatever number you like. It's a variable. It could be 10, it could be 20. I wouldn't say that this visualization technique scales up infinitely. There is a limit to how many dimensions you can visualize at the same time. I don't know what that limit is exactly. It depends on how much screen size you have. But something less than 100 is probably quite a reasonable guess. And these axes, these parallel axes, are represented by these red edges in this image. So there, in this image, there are 1, 2, 3, 4, 5, 6, 7 parallel axes. And each axis represents one data attribute. By the way, this is also true of Cartesian coordinates. In Cartesian coordinates, you have two axes, right? You have an x-axis and a y-axis. And that's the limitation with Cartesian coordinates. You're only allowed to have two axes in Cartesian coordinates. But if you take the x-axis on a Cartesian coordinate system and then you rotate it by 90 degrees and you shift it over by a certain amount, 10% of screen space, that's how you derive parallel coordinates. So parallel coordinates are conceptually the y-axes all made parallel. And the dots that appear in a Cartesian coordinate system show up as edges, these edges that traverse the parallel coordinates. So for example, each polyline here represents one item in the data set, one record in the data set. And everywhere there's an edge intersection, that's the data value that represents. So a dot in Cartesian coordinates represents an edge in parallel coordinates, and then we join the edges together to represent a data record in the data set. Hopefully that will get more clear as we go on. Right, so this is an example of a collection of cars. Right? Imagine we're trying to buy a car. Right, we're trying to pick between SUVs and wagons and minivans and pickups and these other kinds of cars. We have a spreadsheet. In our spreadsheet has one car on every row, and then all the different attributes of the cars are represented in columns. Some of the attributes might be the size, the engine size, for example, the number of cylinders in the engine, the horsepower of the engine, the miles per gallon that the car gets in the city, the miles per gallon that the car gets on the highway. These are all given an axis in the parallel coordinates axis system, and then each polyline represents one car in that data set. So we have a car here with, for example, a smaller car, and then it has an engine size, a very large engine. It has 6 cylinders in this case, and it has about 500 horsepower, and the miles per gallon is quite low in the city, and so on. So each polyline represents one car in the data set. And the advantage of this is we can start to look for relationships between data attributes. For example, there's a direct relationship between city miles per gallon and highway miles per gallon indicated in this plot, right, by all of these many horizontal lines. But if the lines start to cross like this between horsepower and city miles per gallon, it means that there's an indirect relationship. So as horsepower increases along this horsepower axis, the city miles per gallon decreases, right? And that's intuitive as well, right? High horsepower means a larger engine. A larger engine means lower fuel efficiency. And then you can see the opposite is true. Small horsepower usually is associated with a smaller engine. A smaller engine is usually associated with higher fuel efficiency, right? So those direct relationships between data attributes and those indirect relationships between attributes show up in these high-dimensional parallel coordinate plots. And if I lose anybody, feel free to ask questions or ask me to repeat something or interrupt or anything. It's no problem. These plots do have limitations, though. You can already kind of see some of the limitations, right? If you have a very large data set and you just want to visualize it on a naive parallel coordinates plot, you can end up with an image like this, right? It's hard to see anything in this image. It's because there are too many polylines being plotted on the PCP space, right? And they all occlude each other, and it's overplotted. The visual complexity is high, and this is basically what I do. Like my job, or our job, is to come up with innovative ways to visualize data, and that usually means innovative ways to handle large data sets. How do we take an existing technique and then scale it up so it can handle a very large data set? This is how I spend a large part of my life. Just thinking of, okay, how can we take this technique and then make it work when the data set increases to millions of polylines or some arbitrary number? How can we bring it to the next level? And let's look at the demo. So we're going to look at a demonstration of how we deal with large data sets in parallel coordinates, and it's going to be a special case scenario. It's going to be looking at call center data. This is visualizing call center data using parallel coordinates, and each polyline in this data set represents a phone call made to a call center, right? There's an axis here that represents the time at which the call started. There's another axis that represents the time at which the call ended. There's an axis that represents the amount of time each call spent in the IVR. That's that first stage of a call when you pick up the phone and then you start pressing different menu options like dial 1 if you want to speak to an operator or something like that. So I got a question here. Can you only see relations between adjacent columns? The answer is yes and no. The answer is yes if you're looking at a static image. So right now we've only seen static images. I'm about to run a demo video. But as soon as you can start to interact with the visualization, it is possible to see relations between more than one non-adjacent columns. But it does get more difficult as the columns get further and further apart. I hope that the demo video provides some insight into this question. So let's look at the demo video. I'm getting tired of slides, as probably everybody else is. So we'll look at the demo video. Let's see if I have the right one. Let's see, is this the right one? I think that this is the wrong one, actually. I have to get out the smart brushing. There it is. I almost didn't see it. So this is what parallel coordinates looks like in an interactive setting and in an interactive application. This is an industry project. This is a collaboration with a company called QPC based in Birmingham. And they write software that all it does is it collects the data of all the events that happen inside of a call center. And all those events get their own axis in the PCP plot, parallel coordinates plot. And there are different ways to interact with the plot, right? One way to interact with the plot is by clicking on the line, and then you can see the polyline as it spans the PCP space. You can brush, you can define a region, and then all of the polylines passing through that area are highlighted, right? And you can do all sorts of mouse interactions that basically highlight a specific subset of polylines. And this is to help address this problem of overcrowding or overplotting or very, very large data sets when it comes to parallel coordinates. This is a little bit about the data set. Each axis is represents one of the attributes of each call, right? How long it lasts, how long you spent on hold, which agent you spoke to, how many agents you spoke to, and so on. What we did was we introduced this higher order brushing technique that lets the user specify what a polyline should look like, a complete polyline. So, for example, show me all the polylines that pass through this region. And you can see that the user is moving their mouse around and clicking on specific locations in the parallel coordinates plot, and it acts like a filter. It filters, so the polylines that remain fit that brush or fit that shape, but the polylines that are removed are the ones that don't fit that shape or don't fit that pattern. So we can see it starts with with all of the polylines, and that every time the user specifies an attribute range, some of the polylines get filtered out. You can also see distribution plots along some of these lines. Those Those show how frequently polylines pass through that region. We're seeing some of the dynamic properties of this brushing. We call it high dimensional brushing. So the user can interactively adjust the ranges that pass through the high dimensional brushes. And it's generally done from left to right as a kind of, we also think of it like drawing a sketch. It's almost like the user is drawing a sketch from left to right across the PCP space. And by doing so, you can find calls in the data set that are very unusual, right? Calls that follow really, really unusual patterns that really might be impossible to see without this capability, right? In this scenario, the user is specifying two high-dimensional brushes in parallel. This is a comparison between our software and a previous piece of software that's extremely well known called XMDV. We were just basically showing the novel aspect of our approach compared to previous approaches. These are basically enhancements to the basic idea. So we have this high-dimensional brushing technique, and now we can enhance it with some special features like these histograms. These histograms show the number of polylines that intersect the axis in a given interval, right? And that's a special way of visualizing polylines that are overplotting. If they're overplotting, you can't see them, but you still want the information about how frequently they intersect the axis. You can get that information from these dynamic histograms that we can add to the axes of the parallel coordinates plot. We also have these dynamic aeroglyphs, and the dynamic aeroglyphs essentially just point to large sets of polyline axis intersections. So if there's a lot of polyline intersections along the bottom of the axis, then the arrow will point downwards. This is an example of axis scaling. So the user can actually zoom in on one dimension and then scale the axis so that it zooms in on a special sub-portion of the axis, right? It's a zooming operation. It's not your traditional zooming operation, it's a kind of parallel coordinates, high-dimensional zooming operation. And that way you can see more detail on a small sub-region of each axis. This is showing standard deviations. So the first polyline is the average polyline passing through all of the data set, and then the standard deviations away from the average polyline. It's basically showing distribution information because the plot is overplotted, and it's information that you can't see without it being shown explicitly. That's the user expanding all the axes, zooming in all the axes at the same time through a brush operation. So using those standard deviations to define the zoom level essentially. Now this relates to that question, can you see relationships between non-adjacent axes? You can do so by color coding each polyline and then brushing them and seeing how the pattern of color changes across the PCP space. Another possibility, by the way, is to reorder the axes. The axes can be reordered into any arbitrary order. Okay, I think we will stop there. This video does continue a little bit longer. It's basically now showing some examples, some specific examples of specific caller behavior. For example, from customers that are very unhappy. This is us working with the experts, showing them demonstrations of our software and trying to get feedback from them. Right? This is part of our job, is to actually interact with our so-called customers or domain experts and try to get some guidance from them and to see how is what we're doing actually useful, right? And we just thought, you know, it's nice to put that in the demo video. Funny enough, everybody here is now at a different institution. So like Richard Roberts is there on the right. He works for a new company in Bristol. The two guys in the middle also changed companies. I changed universities. So it's a very dynamic set of people there. Okay, by the way, this demo video is also on the DataViz YouTube channel. So if you want to see it again or anything like that, then you're welcome to have a look at the DataViz YouTube channel. And I think now we'll just take questions and answers. I want to thank everybody. I want to thank Luis again. I'd like to thank all of these people. I didn't do all this work. Other people did it essentially. And these are some of the people that have done the work, the actual work. And yeah, I guess, Luis, should we do some sort of a question and answer period now?
Yeah, that's great. I mean, we've run a bit over time, but if people are happy to stay in and have questions that they want to answer, want to ask, I don't think Teams chops us off when we've gone beyond our original thing. So Joseph Best's got his hand up. I don't know if you want to turn your mic on, just ask.
Yeah, thanks. Yeah, Bob, that was a great talk, really interesting and insightful. As you know, the digital research team are building a DataViz community, and I noticed that one of the other really popular subjects that you offered to talk about was DataViz literacy. Is that something you'd be willing to do a talk on with us at some point in the future? Definitely,
yes. That is a topic that is, I would say, it's gathering momentum. Like the more time goes on, the more interest, the higher the interest is in that topic. It's I would say call it an up and coming important topic in data visualization. But yeah, we'd definitely be happy to arrange something. Yeah.
Thank you.
Yes.
We've got one that.
By the way, you can find a very nice talk on data visualization literacy on the DataViz YouTube channel already. No, it's not the same, obviously, but if you want to get a preview, for example, of what it could look like, there are some talks on there.
There's a question just popped up on the chat from Jan Durfus.
What software do we use? Yes. That's a good question because there are many different options. Now, you might remember I said something like my job is essentially, in a lot of ways, boils down to two things. One is innovation, but the other is dataset scalability and dataset size. Usually, the challenges come with dataset sizes. And if you're trying to solve problems involving large data sets, then which technology you choose turns out to be very important. And if you're trying to solve the large data set problem, then our default choices, let's say the default choices for the software we use we use a combination of C++ and Qt to develop our own. C++, Qt, and OpenGL. These are the three key technologies we use when we're trying to create visual designs for very large data sets. Because these are fast tools, they're designed for large data sets, they're well documented, they're free, and they're open source. So they really fit the bill. That doesn't mean we only use Qt, C++, and OpenGL, though. We do have a project now working with JavaScript and other web technologies, web-based libraries. And the idea there is to make it a little bit more, I guess, user accessible, right? A lot of people, there's a large demand for visualization software that is accessible to a large user audience. And if that's one of your priorities, then web-based technologies are a good choice for that. Like a very popular web-based technology is D3, very, very common visualization library for the web. However, you do run into challenges in terms of scalability. So web-based visualization is generally not as scalable as, let's say, desktop-based visualization. Would you recommend any GUI-based tool for producing high-quality visualizations? Oh, I see, yeah, the off-the-shelf tools. So, you know what, that's a non-trivial question because the number of off-the-shelf tools is exploding. But I can say that I have given tutorials using a tool called Tableau. So Tableau happens to be really, really popular and is gaining in popularity rapidly. Most universities, I think, have a license to Tableau now. And I have some Tableau tutorials on the YouTube channel as well. But you can find collections of tools. You can find huge collections of tools. There are some special web pages. Yep, Tableau is, last time I checked, Tableau is also free for students. And it might even be free for researchers. It might be free for non-profit, essentially. But yeah. Tableau is one recommendation I can make. I can also mention that Excel has a lot of visualization capabilities that most people don't know about. I think most people's kind of knowledge of Excel is outdated. Most people think that you can only make like pie charts and bar charts in Microsoft Excel, but they have a lot more options now, and they're increasing their options. I think they're trying to get up to date in this space and be a little bit more competitive in this space. And they have a lot of interesting options now. Yeah. Okay. Exchange Nottingham. I'm not sure what that is. Okay. New analytics platform available to UK staff. So maybe I should check out that link. Okay, I'm getting a 403 for some reason on that. I don't know why. That's very strange. Anyways, I'm sure that the link actually works somehow, somewhere. Yeah, I don't know why it's not working for my web browser. Any other questions or comments?
There's another one about halfway up your chat page from Joseph Best.
So really, would you say it is more about applying the correct technique then rather than the specific tool? Yes, I would say that. For any analysis, if you're working with, say, a third party, it's really the most important thing I would say is to start out by asking questions. Basically, we always ask the same questions at the beginning of every project. We try to talk to the people that were involved in collecting the data in the first place, and we ask them questions like, why did you collect this data? What kind of questions were you trying to answer by collecting this data? Did you develop any hypotheses that you were trying to confirm or refute when you collected this data? This is the ideal case scenario. That's not the reality, but that's the ideal case scenario. A lot of times, in my experience, a lot of times, this is actually the average case, the most common case. The most common case is, dear Bob, we have collected this massive amount of data. We don't know what to do with it. Can you help us? That is basically the starting point for a lot of projects, including the QPC project we just looked at. They said, we wrote this really fancy software, this really fancy database software. It collects millions and millions of call center events, and now we don't know what to do with it. We don't know how to analyze it properly. We don't know how to visualize it properly. Can you just help us? And so there's an ongoing dialogue that's there. And a common reaction I get is, well, we don't know what we want either because we don't know what visualization is capable of. So they say, can you make some suggestions to us about what's possible? That's often what happens in reality, which is a good thing. You know, it's a good thing because that gives us a lot of flexibility. So that's one advantage. But it's not a good thing in that it's an unconstrained problem. And so we often will present solutions that might not be particularly useful, that can happen, that are particularly useful for the industry, the domain expert involved. This is a good audience. It's good that we have Joe here. Well, way more questions than I was expecting.
I think you've got another one at the bottom there.
Okay, have you used Power BI? I have not used Power BI personally, but I have certainly talked to students that have used Power BI. From what my impression is that Power BI is a descendant of another tool called Many Eyes from IBM. IBM used to have this open tool, free visualization tool called Many Eyes. It was extremely popular, and then the developers left IBM, and then the tool died when the developers left. And Power BI seems to be a response to that. That's my impression. But certainly, I've had students use it. Certainly. This is a challenging topic because the number of tools has exploded. There are over 100 tools available now. And then it's like, well, how do you decide from this jungle of tools what to use? I suppose maybe the situation will improve in a few years and like some of the tools will die off, the ones that aren't that great. And maybe the pool will shrink to a manageable level at someday. Who knows? Who knows what's going to happen actually? Did I answer that one? There are academic licenses for £5 a year. Yep. I know in my experience, we're usually looking for free tools. And the reason we develop our own tools is for the innovative aspect. So with the tools that are existing, there are always limitations in terms of data set sizes that they can handle and the features that they can actually support. So we're always looking to test the existing tools, see what their limits are, and then find out, okay, how do we overcome these limitations? This is a common pattern that we see over and over and over again. Yeah. I'm surprised there are people that are still alive. You guys have really good stamina.
Well, I was just looking at, we've still got 32 people on the call, so so if you're happy to carry on answering questions, then
yeah, I don't mind. I don't mind. I remember I gave a tutorial once that was 4 hours long, and I didn't realize I didn't really have that much experience, and I actually I didn't lose my voice completely, but by the end, it was pain in my throat. Like I couldn't talk. Not that we're not going to go on for 4 hours, but
I don't think we're able to that. There's quite a long one here. I think that's more of a
comment. Yes, if anybody's interested, I can show you. I forgot. I'm not used to this way of presenting. So I will show you where you can find huge collections of tools. So if you can find my webpage. I hope that I've got this up there. I think I do. If you click on my teaching page, hopefully this works. And then you click on the data visualization lecture, the data visualization module. I have a web page for the data visualization module. It's still under construction. But so it's got links to the DataVis channel. But look, the second 2 links are collections of tools, and they're ridiculous. So this one is, I don't know how to pronounce it, keshif.me. But this is a collection. Somebody worked very, very hard on collecting off-the-shelf data visualization tools. They work so hard that it takes a while for the web page just to be loaded because it has so much information on it. These are all well, they're not all off the shelf. Some are for developers. Some of them are for off the shelf. So there are different filters here, right? This happens to be programming, but if you look at the top left, you can see that there are 431 tools here altogether. Data visualization tools and books. So it's really, it's a huge collection, really, really huge collection. And this is only one of them. There's another collection on my webpage. This is from visualizingdata.com. Keeping up with what's going on is a challenge in itself, by the way, and keeping up with what's going on is one of the projects we're working on now. So here's another set of tools, and you can sort them by their different attributes. For example, if you want all web-based tools, you can click on the web-based tools, and you'll see that there are quite a lot of them there. And again, there are so many that it takes some time just for the web page to load because the collection is so huge. Yeah. So lots of different options. Lots of different options. It's a jungle out there, actually. It's quite a jungle.
It's really interesting. I think people are sort of dropping out now because they've gone on a bit longer than we said we were going to originally.
Yes.
So I guess sort of my question is if people have visualization issues that they're trying to solve and whatever, are you happy for people to contact you? Am I opening you up to
yes.
email?
If you have visualization projects that you're interested in, feel free to contact me. I'm new at the university. I don't know anybody, so I'm always happy to meet new people and I'm trying to form some sort of a professional network here in Nottingham. So feel free to contact me. I'd be happy to be a member of your network. And I'm happy to join Nottingham, basically. I think Nottingham is happy to see data visualization arriving at the university as well. Yeah.
Yeah. Well, that's, really interesting talk. Thanks. You can see you've got lots of votes of thanks arriving on your chat. So it's brilliant. So I think people are sort of leaving. So we'll call it today, I think, probably for today's session. If there are still people out there and anyone else fancies doing a talk for the network, then we're more than happy to take people's ideas. So I think the online thing's worked well. So we'll probably try it again.
Yeah, it worked out better than I thought it would. Yeah. Thank you everybody that watched. I really appreciate that, and thank you very much, Louise, for organizing it.
It's okay. Thank you very much. I can see all the chat coming up saying thank you. So I guess I just close the call. Okay.
Keep in touch.
Bye, everyone. Yeah. Okay. Bye.